Logarithms. As you may recall from a previous math course, logarithm functions are inverses of exponential functions. Therefore, logs inherit the analogs, or the inverses of all the properties of exponents. Thinking back, if you have like x squared times x cubed, you'd keep the base and add the exponent. Or if you have x squared raised to the third power, you would multiply those exponents. So logarithms act very similar to exponents. In fact, what is the definition of the logarithm? Look at this definition. The logarithm of a number is the exponent to which another fixed value, the base, must be raised to produce that number. I know that's a lot of words. It says here we have that, if and only that. Look at how that's related. The log of a number equals the exponent. The log of a number equals the exponent. Here's the exponent. So that's why logarithms and exponents are tied together. We also have what's called the natural logarithm, and that's where we get into base e. Base e is an irrational and transcendental constant. It's approximately equal to that. No, you don't need to memorize it, but it's close to 3. And so where we would have logs in our calculator, when you see log in your calculator, that is in base 10 because our number system is in base 10. And then you have a natural log button on your calculator, and that is base e. This is more commonly used in your math and science courses. We have several properties of logarithms. You should have seen these before. You might not feel comfortable with them, but we're going to practice and review. We have an inverse property that's very handy. Look what it says. We have the log of base b of b to a power. You just get the power, meaning the log and the base cancel each other out as long as those bases are the same. And here, if we have a base raised to the log of the same base, again it cancels out as long as x is positive. Then we have a product rule, very much like the exponents. Again, the bases have to be the same. If you have the log of a base of a number plus the log same base of a number, then you can rewrite that by multiplying those together. And that comes from this exponent rule about adding those exponents together. Quotient rule, you can divide, again, as long as you have the same base. Then we have a power rule saying if you have a number multiplied by a log, you can make it into the power. And then we have the change of base rule. Depends on what you're doing of whether you would have ever used this before. But because our calculator only has base 10 log and base e, this would be nice to know if I wanted the log base 4 of, say, of number 21. I could use that change of base formula and then use my calculator by making a common log, say like log base 10, and rewriting that as log base 10 of 21 divided by log base 10 of 4, and then using my calculator to approximate what that value is. And that's how that change of base rule is used most often, is with the calculator. But let's go beyond that calculator. Let's look at some of these problems. We're going to evaluate. When you see the word evaluate, that means you're going to get a numerical answer. And a lot of these are going to first use this inverse property. We have base 2 here, base 2 here, just like this property up here. And so if we have log base 2 of 2 raised to a power, that inverse property says then it's just that power. Problem number 2. The natural log is base e. They don't put the little e, they put the ln to tell you that's base e. And again, we have that same inverse property just like problem number 1. We have the log of the base, same base, raised to a power. It's just that power. Right, number 3, again we're in the same base, but it's this inverse property right here. If we have a base raised to the log of the same base, they are inverses of each other. They cancel each other out, and you just get that 8. Now number 4 and 5, we're going to put together a couple of these rules. Number 4 looks like this rule. We have the log base 6, the log base 6 of two things added together. And this property says we can combine those by multiplying. But can I go further? Yes, I can. Think about, I'm in base 6. How could I write 36 in terms of base 6? Well, isn't that 6 squared? And if that's 6 squared, isn't that problem like number 1? Where we have the base cancels each other out. So that's just equal to 2. Now these problems are contrived so you can learn these rules. That's all there is for them, so we can apply them later on to different equations to solve and different application problems. All right, let's look at problem number 5. We have this exponent that looks like number 4. So let's go ahead and write 5 right here. Then we have log base 5. We can multiply that together. 6 times 7 is 42. Now we have a problem like number 3, in that we have the base, the log of the same base, raised to the power of the log of the same base. They would cancel each other out. So I would just get 42. So those are pretty easy problems, something you should have done in a college algebra class. This next problem is a little bit more challenging because we don't have the same bases. And we don't have any rules that involve different bases, except for this change of base rule. So let's see what happens. If I write this using the change of base rule, it says I can put the log of x, so that would be the 6, over the log of the base, which would be a. Now when I just write log, that is implied to be base 10. We could have also just used the natural log, which is implied to be base e. Now I'm going to rewrite this. I'm going to multiply that. So that's log base 10 of 8, that goes on top, divided by log base 6, which goes on bottom. By multiplying, those can divide out. So I have log of 8 divided by log of 2. No, you cannot say that's 4. There's no rule that says that. Go back and look. Doesn't have a log over a log. The only one that looks like that is that change of base formula. So let's go backwards. So I can say this is the log of 8 base 2. Going back, the base goes on the bottom. The base goes on the bottom. So now, what about that one? Let's go back to number 4. We kind of sort of had something like that. So let's think about how could I write 8 in terms of base 2? Well, that's 2 to the 3rd power. And now we have log base 2 raised to the exponent just equal to the exponent. So lots of different ways you can use those inverse properties, things like that. And we will practice those and apply those more later on when we get to solving equations. Within equations, it's also nice to know how to expand logarithms. When you get to Calculus 2, you'll be very happy you know these properties. It's going to actually make your problems easier. So here we're asked to use properties of logs to expand the expression and simplify. Well, look at what we have. We have the log base 5 of something divided by something else. So we have a property that says we can subtract. We can rewrite that as the numerator subtract the log of the denominator. Can we go further? Yes, we can. When you see a radical, you really should rewrite that as a power. And then the last thing we can do is use our power rule and bring that down in front. And could we go further? Well, I would say yes, you can, but it'd be kind of tricky in that you would have to notice that you could actually factor that expression. So if I factored that expression, I would have log base 5 of x minus 1 times x plus 1. And then since I have two logs being multiplied together, I could rewrite that. I would say minus the log base 5 of x minus 1 plus the log base 5 of x plus 1, because I'm using this property, a times b, could rewrite that as the log of a plus the log of b. And then the last thing I would do is distribute this minus sign. So probably should have factored way back there. Didn't really see it at first. So can I do anything else? Can I do a power? No. I can't do anything with that. You cannot distribute the log. It is not something you can distribute. It's like a square root. It's either the square root of the whole thing or the log of the whole thing. So this would be the same as that. By using those properties, we use the property where we could subtract, the property of the multiplication, we use the power rule. So we used all three of those. All right, let's try the next problem. Same type of thing. We're just going to have, you notice we have this multiplied to that, divided by that. And we have the natural log. That's just base e. So we're going to start out with the same property here, subtraction. So this would be the natural log of 5x squared times 1 minus x to the 1/2 power. I'm going to go ahead and take that square root as a half power, minus the natural log of 4 times x minus 1 squared. And that's the natural log of all of that. Now I'm going to use the multiplication property and separate those. So I have the natural log of 5x squared plus the natural log of 1 minus x to the 1/2 power minus the natural log of 4 plus the natural log of x minus 1 squared. That subtraction needs to go to both of them. What about here? Could I separate that? Yes, I can. So I could write that as the natural log of 5 plus the natural log of x squared plus the natural log of 1 minus x to the 1/2 power minus the natural log of 4 minus the natural log of x minus 1 squared. And really the last thing I'm going to do is I'm going to use my power rule that says if I have a log of something raised to a power, I can bring that power down in front. And that would be my final answer. Now look at number 9. What could we do? What can we do with that 3? We could do a lot of things. We could actually bring it down in front first. That's one option. Or we could rewrite this as 2x plus 1 cubed divided by 3x minus 5 cubed. How would you like to approach it? You're going to end up with the same thing either way. So go ahead and finish this on your own, and we'll compare notes in class. On number 10, we're going to use the properties to rewrite this as a single logarithm, meaning we're going to go backwards of what we just did. So speaking of going backwards, the last thing that we did on those last problems is we brought the numbers in front, well, the numbers as an exponent down in front. Since that was the last thing, now we're going to use that as the first thing. So we're going to rewrite this as the natural log of 3x plus 1 cubed minus the natural log of 2x minus 1 squared minus the natural log of x. And do you remember what the half power is? How do we write that? We could write it as a half power, but let's go ahead and write that as a square root. Then, from working from left to right, we have a subtraction. So we could write that as the natural log of 3x plus 1 cubed divided by 2x minus 1 squared. Now that's the natural log of all of that. Then I have to do the subtraction again, so I have to divide. Well, do I make it a big fraction? No. Where is that going to go? Well, when you divide, it's going to end up in the denominator, so that's going to be the square root of x and 2x minus 1 squared. So again, we can go backwards. Now problems in 11 and 12 look really weird, but again, it's really a pre-calculus topic. You're going to be doing a lot of this when you get to calculus, solving different types of things that you don't know about yet, but you will need to know these logarithmic properties. So here on number 11, we want to express y as a function of x, meaning we need to get y by itself. How can we do that? Well, we have the natural log on both sides. So if the natural log of a equals the natural log of b, then that implies that a equals to b. So here we could just see y equals to x plus c. Yep, that's it. Not much else. Well, there's got to be something more to that, right? Well, we still want to get this. We want that to look like that. That means we've got to do some work on the right-hand side. So let's look at those. We could rewrite that as the natural log of x divided by x plus 1 because of that subtraction rule. Then the next step, we can rewrite this because it's plus, we can multiply that together. So that's the natural log of cx over x plus 1. And then I can use this property that a equals to b, so y equals cx over x plus 1. It's kind of strange. Just go with it. Again, it's just using all these properties. The inverse property, the product rule, the quotient rule, the power rule, and that change of base rule.